Okay, let's get started. Just to make sure, I know Hannah and Valerie have rented lab guides. Does anyone else have a rented lab guide?
Me.
You do?
Yeah.
Okay, let me just give you.
Oh, I got mine. So I don't have to print them anymore?
Yeah, because it's a better copy. I tear them out and photocopy them.
Okay. Thank you.
As long as you have it rented, right? Because it's not legal for me to give you those if you don't.
Gosh, I was going to say, well, what's the point? But yeah, it's right there. Cool.
Okay, so the lab we're doing today is entitled Float Boat or Boat Float. And we're going to be following along the instructions with some minor changes. So minor changes here, instead of a spring scale, we're going to be using this force sensor right here. So we're using the Pasco force sensor. And we're not using masking tape. We have these graduated cylinders here. This says 600 milliliter breaker. We're using the graduated cylinders. You don't really need to mark these or anything. I'm just specifying things that are different. Instead of a clear container this is a clear container, right? A toy boat, we've got the little wood blocks. The wood blocks I found in preparation really unstable. It took a lot of effort to try to get it balanced on there. We're not going to use a balance. We're going to make all of our measurements using this for both mass and weight. There's the graduate cylinder right there. Okay, so we're just using that. Water, we've got water. Mauling clay, we've got mauling clay. And then we have masses or fishing weights. So those are the stuff. What we're going to do is we're going to examine Archimedes' principle. So Archimedes, and now I have a little more time. I can tell you the story, except for I think it was Jocelyn. I was telling the story to you yesterday already. So the story is that the king, I don't remember who the king was, took a chunk of gold. He took it to a goldsmith and said, "Make me a crown." So the goldsmith made him a crown. He got the crown back, and then he said, "I don't trust that thieving goldsmith. I think he ripped me off." He takes the crown to Archimedes and says, "Can you tell me if this crown is made with the gold that I gave him, or if he did something, to cheat me?" And so Archimedes, like any smart person, says, "Well, first thing I'm going to do is measure how much it weighs. Because if it doesn't weigh the same, we'll know that there's something amiss here." He measures it weighs the same. And he's like, okay, so that's not proof. It's just kind of like coincidence. What would really help me is if I knew the density. Because gold has a distinct density. We had to use it for one of the homework problems. What was it, 51.8 or something like that, grams per centimeter cubed? So if it has the right density, then I can know, yeah, it's probably pure gold. And so he's thinking, now how can I determine the density? Can't just, measure how tall it is and how thick it is, because it's got all kinds of elaborate stuff on it. So he's, I think best in the bath. Draw me a bath. And so people fill up the bathtub for him. And as he gets in the bathtub, he notices that the water rises when he gets in. And he gets struck with a wonderful thought. And he jumps up and he shouts, "California!" Okay. Eureka, because that's California's motto, right? Everybody knows California's motto. Eureka means I found it. And as the story goes, he then goes prancing down the street, all excited, forgetting to put on his clothing, because he figured out how to solve this. Because he said, when I got in the bathtub, the water level rose. Why did it rise? Because I was pushing the water out of the way. And the amount of water that I pushed out of the way was equal to the volume of me. And so I can determine how much water, or if I sink the crown in water and measure how much the volume changes, that tells me exactly what the volume is. Already having measured the mass, density is just the mass divided by volume, he could determine if it had the right mass or density. So he did the measurements and it had the wrong density. And then they cut the crown apart and they found that he used vines to make the structure and then just put gold around the vines and kept the excess gold as extra profit. Now, probably not a true story, but it lays forward the Archimedes principle. And Archimedes principle says when you put something in water or another fluid, it will displace fluid, and the weight of the displaced fluid will weigh exactly the same as the upward buoyant force the fluid applies on the object. So if, for instance, you jump in the swimming pool and you float, the water level rise, you measure the weight of the difference there in water level, that's equal to your body weight. That's what Archimedes' principle says. So we're going to be exploring that today. Question, Tiffany?
How does one measure the weight of the water?
Well, in the swimming pool, you don't. I mean, you could imagine, okay, so we have a swimming pool that's filled up just to where those little overflow things are, and then you collect all the water that overflows and you weigh it. Kind of contrived because you're not really going to be able to do that well, right? We're going to be able to do a better job at here because we're in the lab and we have appropriate equipment. So what we're going to do, you see here, procedure, step 1. Using a spring scale, well, in our case, that's going to be one of these. We need to make sure that this is vertical when we make our measurements. I made the mistake of not having it vertical when we made our measurements earlier. Fortunately, Alex was paying attention. He said, is that going to be a problem? And I said, yes. So make sure you have that vertical, and we're going to measure the weight of the object in water. So we go here to the Pasco capstone. We're running I couldn't remember which experiment number it was, so I put an activity XX boat float. And so you need to have the force sensor connected, as you can see, force sensor connected. And the first thing I want to do is to make sure this thing is calibrated right. Calibrated right means it's going to measure the right numbers for weight. So I go here to see that green calibration button. Say yes. Yes, we are following along. And it says, choose the type of measurement you would like to calibrate. Force. So force, next. The type, we want it to be the 2, which is the one that comes up by default. Next. And then we have the first point. To do the first point, I'm going to have it just like this. How much is hanging from this? 0. Now, before I go any further, I'm going to go ahead and press this button here that says 0. That's just going to make sure that it reads 0 when it's in this position. And now you can see down here this number. This number is telling me, what the value it's reading right now is. I press set current value to standard value. And now I'm going to use a standard value. And it defaults to 50 newtons. Well, I am not going to calibrate it with 50 newtons. We're going to be working in the range of around 100 newtons or 100 grams or less. So I'm going to take 100 gram mass. What's the weight of 100 gram mass? That's its mass. What's its weight? Yes, the weight is the mass multiplied by the acceleration of gravity. There we go. None the worse for wear. So I'm going to take this, put it on here, and now I'm going to change that from 50 to 100 times 9.8 would be 980. I'm not going to put it in 980 because this is in grams. What's the standard unit for mass? For mass? It's not grams, but it's close to grams. Kilograms. So this here, the number was grams times meters per second squared. If I wanted newtons, that's kilograms, and so it's actually 0.98 newtons. So now that I've put that in, I click to set the current value, and now it's calibrated. I just click finish, and it's good to go. I'm good to do my experiments. Now I'm going to do a trial here like you're going to do. So I have a piece of string here so I can hang something from it. I'm going to hang the string from here, and with the string and nothing else hanging, I'm going to press the 0 button again. Notice the string has a certain weight to it, right? So I'm zeroing it with the string so that that won't be counted against me.
Right.
And then I'm going to take this object here and hang it. So make it so it's not swinging around. Rotating is not a problem, but not swinging around. Hit the calibration button to get rid of that, and just hit record on the data. And notice two things. It's showing me numbers over here. You can see it's going between roughly 830 and 832. And there's a graph on the other side. I'm going to come over to the graph and click the button to see the statistics. And it says the mean value was 0.831. And so what is the weight of that baby? 0.831 newtons. So that's my first measurement. Actually, where did we put the one we were working on, Alex? Where did we put the one we were using when we were working on the experiment? The lab instructions? I want to not have to ask them. Now, what does it say next? What does it say next? And granted, I have them. Okay, so the weight of the object out of water we just measured, 832 newtons. Now the weight of the object in water. So I have this graduated cylinder, and I'm going to put it in the water. Before I put it in the water, I'm going to do part of what's necessary for the next step. Notice step 2. Step 2 asks us about how much water it displaced. Well, this graduated cylinder is going to allow me to determine that, because if I measure the volume of the water before I put it in and the volume of the water after I put it in, the difference will be how much water displaced. So I'm going to measure the volume right now. So I get down here. Notice it has numbers, and up here it says milliliters. Each one of the little steps is 5 milliliters. So it says total 500 : 5 milliliters per step. So right now it's just below, well, it's about halfway between 360 and 365. So let's say 362.5 is the volume right now. Lift this up, put this under, put it in. Make sure that you don't have anything touching the graduate cylinder. That's all just in water and not touching the edges, including the string not touching the edges. I'm going to measure the height again, and now it says 390, about 391. So 391, let me just go back to here. So we have 391 milliliters, 362.5 milliliters. So the volume that it's displacing is just the subtraction of those two numbers, which would be, yes, 28.5 milliliters. Now, notice on this, I did some work on the side. You're going to have to do a little work on the side here. They didn't give me really enough space to do everything on this one. The weight of the object out of water, that number was 0.832, and that was newtons. Now the weight of the object in the water, all I've got to do is come back here and hit record again. 539 is my average, 0.539 newtons. So I have the weight when it was in air and the weight when it was in water. It's very clear it was a higher weight in air. Why is it a lower weight in water? Because water's what? The water is buoyant. The water is providing an upward force. We call that the buoyant force. And so the difference in those two numbers is going to be the buoyant force. Question? Okay. So all I have to do here for the next line is just subtract them. So 12 minus 9 is 3, 9, 2. So we have a buoyant force of 0.293 newtons. Yes?
Should we be copying this down, or are we going to have to?
No, you're going to do it yourself. So you'll have different numbers.
Okay.
I'm showing you how you're going to do it. Now the mass of the water display, or the volume of the water displaced I have is 28.5 milliliters. What's that mass? We've learned the density of water. We learned that the density of water is equal to 1.00 grams per centimeter cubed, right? Density is the mass per volume. So if I want to find mass, the mass should be the density multiplied by the volume. But the problem is my volume's in milliliters and my density was in grams per centimeter cubed. Anybody know how to fix that? And this conversion is the hardest one ever. Convert by multiplying by 1. Which means I can do this math without doing a calculator. I just say, that must have been 28.5 grams. Excuse me?
That's how we work 1 point.
You don't need to show your work for that calculation. Okay, then it says weight of the water displaced. How do I get the weight once I found the mass?
Times gravity.
So 28.5 grams is 0.0285 kilograms, because kilograms is the standard, times 9.8 meters per second squared. And so, handy dandy calculator. Or I could ask Eric.
No, I can't do that one. At least not quick.
0.279 newtons. Now, according to Archimedes, what should the weight of the water displaced equal?
Exactly the same.
Exactly the same as the weight of the object. Are they exactly the same? No. Are they close enough to be convincing?
Yeah.
Some say yes, some say no. That's why we don't do just one trial. Now you're going to be asked a question, right? The next page says, how do they compare? And so you need to say, are they close? Are they the same? Are they very far apart? Right? That's your statement about how close they are. The next thing here, to simplify calculations for the remainder of this activity, measure and determine masses without the need to find the equivalent weights. Okay, so I'm going to change right here because I didn't even read that before. I was saying, since weight is mg, we can take this and recalibrate it so it's going to show us the weight divided by 9.8 and just give us the mass in grams. So I'm going to go ahead and recalibrate this right now. So take this out and go back to the calibration. Calibration. Forced calibration. Let's see, does it have? Yeah, no other option because that's the only sensor. Use the standard 2-point again. Next. 0, even though it says newtons, I'm going to ignore the newtons and say that's 0 grams right now. Make sure I press the tare button, the 0 button, and take a measurement. Put this on, and how many grams was this? 100 grams. So what do I put here for my standard value?
0.98.
Because I'm doing it in grams, 100. 0.98 is the correct force. So now it is calibrated in grams. So just for recording purposes, now it's measuring 100 grams. It says newtons, but it's actually calibrated in grams. So for the rest of the experiment, to make life easier so we don't have to do all those calculations we were doing, Alex, it's just going to already have the weight divided by G to give us the mass in grams. So what do we do now? First, we have use a balance to measure the mass of a piece of wood and record the mass in the data table. Measure the volume of water displaced when the wood floats. Record the volume of mass in the water displaced in the data table. Where's the data table? Next page. So this first line, the wood. So for the wood, I'm going to take this piece of wood and I'm going to make the same exact measurements that I made before, except for one thing. What's the wood going to do when I put it in water? It's going to float. So when I put it in the water, how much is the weight going to be? How much is this going to measure for the force when I have it in the water? It's floating. 0. So you're going to have the measurement you have in air. Oh, remember you need to tare it before you put the thing on. I screwed that up. So I put on here, hit 0. Now I put this on. And I'll measure its weight in air. Of course, you don't want it swinging around like it has right now because it'll have varying forces. I'm just going to do it anyway because my data doesn't really matter. Only yours matters. You could see the numbers fluctuating a little because it's swinging around, right? That's why you don't want it swinging. So we have it's 12.0 grams roughly. Now I would need to, and I'm not going to make the measurements to save us time, I would need to measure the volume of the water before I put this in. The volume of the water will change over time because of A, evaporation, and B, every time you dip something in and take it out, you're taking some water out. So you do need to measure the water you start with each time, and then you put this in. Now remember before I said don't let it touch the sides? I don't have a choice when it's floating. It flops over. That's okay because it's floating. I measure the volume again. I'll get the volume displaced. What should I get when I measure the force here? That's what it should be. Let's make sure. That's worrisome. It's close to 0. It's a little bit different. Why? I don't know. Clearly, that's our experimental error at some level. So we have our measurements here of the mass. And so in this case, the mass was 12.0, right? That's what I measured in air. And the volume displaced, I have to have the two numbers. So I would have, let's say it was, the second number, let's say, was 378. The first number, let's say, was 365. I'm just making these numbers up. And so the difference in those two is 13. And so what would the mass be if it's 13 milliliters? Notice it says milliliters here, so I don't need to write the units.
13?
Bueno.
Wow.
We're good at that math.
I feel like I should get credit.
You should. Now the next one we're going to do differently. The next one, it says wood plus 50 gram mass. We're not going to use this for the wood plus 50 gram mass. For that, we're going to do this. And I have in there a 50 gram mass on top of one of these pieces of wood. And here I'm going to just put another one. And if you look at them, what I want you to do is simply make comments about how high the wood is floating. That is, where's the water level on the side of the wood? So comment on where the water level was in the side of the wood when there was no mass on it, and where it was when you had 50 grams sitting on top of it. Question?
Are you wanting us to use 100 grams or 50 grams? Because the one sheet says 100, but the table says 50.
Let's use 50 because it would sink that thing if I used 100.
Okay. Because if you look at step 4, it says 100.
I hadn't even noticed that because I stopped paying attention to the sheet and just looked at the table when I was going through. Good eye. Yes, I see. At 100 gram mass. Well, we added a 50, but we did it differently. Now the next step, you're going to grab yourself a piece of clay. You might want to make your clay smaller than mine because you're going to have to hollow it out for the second part. So I'm going to make this half of what I did before. The first thing you do, make sure you don't have any air bubbles and roll it up into a little ball. And as you're rolling up into a little ball, take your string and embed your string in that little ball so that it will be tied to it. Got it? Mm-hmm. Then you do the same measurements again. So you're measuring the weight in air, the weight in the water, the volume displaced. That's trial 1 with this. Trial 2, you take the same thing and you hollow it out. Now notice our graduate cylinder is pretty narrow. So basically what I did was I took this and molded it around my finger to make a little bucket. And it took me a lot of tries to make my bucket big enough that it would actually float. And then to get your finger out, you have to be a little tricky, or else you'll just be getting your finger out. So now I have my little bucket, and if I drop it in there, it's never going to float. So I need to, once again, just embed my string on there so it won't drop in. Hopefully I have it hollowed out enough to float. Almost, not quite. So I would need to take it out, make sure I get all the water out, make it a little bigger so that it does float. When you have it so it floats, you're going to again make the measurements for the floating. Notice it's the same weight now. What's different about it is you hollowed it out, so it's going to displace a different amount of water. And so that's where the floating clay is. The floating clay is where you hollowed it out. And then you just have questions to answer about the experiment. And this here is thought. Actually, no, it's not thought. This here is, well, we're not going to do it. Let's just not do it. So, not doing page 70.
Amen. Praise the Lord.
I should be a pastor. I'm inspiring the flock. Any questions? The last one. That's probably a lot. Okay, but you want to ask them later?